Hey, students, I just got a question on, I think, one of the harder ones here from this chapter 24. Let me dive right into it. It looks like it's chapter 24, number 41, but it really is a what they call an integrated problem. They're asking us to go back to Doppler effect. So I looked that up. It was back when we did the sound waves in section 17.4. So you might want to go look at that. They've got some nice pictures, and I printed up this equation. And so what this equation is F sub s is the original frequency, but then the observer is going to get something a little different. And there's two factors. There's this factor, which is the shift because the observer is moving, and plus or minus depending on which way the observer is moving. And then there's this factor, which the source is moving. And so in this problem, we kind of have both here. If you kind of draw a little picture here of maybe the police car heading down the highway, and they're behind you. And they have this little radar dish, and they send out these waves. You might say at first you're the observer. Of course, you can't detect with any human sensory the radar. Although some people use those little radar detector things on their dashboard, and they pick up the scatter radar. Although you don't see them much anymore. Well, no point, because at least in California, all the CHP officers now have switched from radar to LiDAR, so their radar detectors are useless. But there would be this shift. So you would observe a different shift. Then you would reflect off. Let me go to a slightly different color. And now you would become the source of the radar waves. And then they would be detected by the other part of the radar equipment on the CHP or the policeman's detecting system. And so now you're the source, and the police car is the observer. So we have both shifts going on. We have a shift because part of it is shifted because you're the observer, and then again, you now become the source, and there is then you are a moving source. All right, so let me kind of put in these numbers using what the analogy of our sound waves. And they gave us the frequency of these microwaves. And so the original frequency, that is the electronics in the box here in the police car, make 1.5 gigahertz. So that's this first factor, what I'd call the real frequency, the frequency of the source. Okay, but you observe a little shift because you, again, at this point, collecting it, being the observer, are going to collect a different frequency. And so this V sub W is the velocity of the waves. And it's a downward shift when you're moving away. So you as the observer are moving it away. So I'm going to put the minus, and then this would be V. Let me just call it V, the velocity of your car. And that's what the police car is trying to detect, this V. You're now, at this point, when I'd say you're the observer. And so whatever this math comes out to be, this would be the frequency that if you had a detector, or if you could detect them with your human sensories, you would say that's the frequency. It's not 1.5 gigahertz. It's been shifted down a little bit by this much. But it's also going to be shifted yet again, because now thinking of the reflection, this whole thing right here is now being the source, going back to another observer here. And so I would say the source is now moving away from the police car. So I'm going to put the speed of the wave. So there's a C, there's a C. And in this case, the source is moving away. And so again, going back to section 17, we would put the plus sign for the velocity of the source. Now, the source is the velocity of the car, so I'll just put a V there. So in this double shift, and they even helped us out with the wording. They said a double Doppler shift. Okay, so there's a shift because we first observe it and then reflect it off. So now we become the source. So we're both an observer, then we take whatever we observe, we reflect it back. So now we're radiating that source, and we are moving. So we're a moving source. So we're both a moving observer and a moving source. So that's why the phrase double or Doppler is shifted. So they were trying to help us out by throwing that that in there. Now, fortunately, mathematically, those cancel off. Now, the other piece of this is to say that it is shifted a little bit. Now, again, we're moving away, both in terms of an observer and a source. So this would be the 1.5 gigahertz minus, and that's what that beat frequency is. So another thing we need to kind of get out of the chapter 17 is that the difference in two frequencies, and I did them with those sound tubes hitting the tuning forks, and you heard that wong, 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 wong. Okay, that's the difference in the frequency. That's the beat that would be picked up. And so the observed frequency would have been reduced by 150. Now this right here leads to kind of a mathematical challenge. And I was kind of wondering when I got this question if somebody was asking about the physics behind it, because it was something we did last semester in chapter 17. It's been a while, and we didn't spend much time on this. Actually, at summer school, we didn't spend much time on anything. But there's also some tricky math. Because, see, this has 9 zeros, and this only has 3 zeros. And so how do you take that minus that? It's really a small, small number. Now, we could get out our calculator and probably do it, but I looked over at the solution manual, and they did some simplification to deal with this. See, what they did is they moved this to the other side. And so they got 1.5 times 10 to the 9th minus 150. And each of these are over 1.5 times 10 to the minus 5. And then, of course, this side simplifies to C minus V and C plus V. And if you do that, things get a little bit simpler here. You could then say this is 1 minus 150 over 1.5 times 10 to the 9th. I suppose you could even do this, 1 minus, and I'll put 150. And over here I'll do 150. So I'll move the decimal 2, so this becomes 10 to the 7th. And, of course, what's nice about this is 150s cancel off, and then it's times 10 to the minus 7. So this is 1 minus really, really small, 1/10,000,000th of it. So your author plays this little trick. And part of me says maybe I should just avoid the trick and just cross-multiply. I got a C minus a V here, and I got a C plus V. But since I think somebody might be asking about what the math the author did, let me kind of look at what the author did. And that's why I guess I saved myself some yellow paper here. Let me do this. Let me multiply the top by 1 over C and the bottom by 1 over C. Because if I do that, this becomes 1 minus a little bit. And this becomes 1 plus a little bit. See, it's the little bit. So we've got ones and a little bit everywhere. And because of that, we can end up dropping off the ones on both sides and just comparing a little bit with a little bit. And that's the approach your author took. And so let's call this V over C. I'll just call it a factor of X right now. And say that's a little bit. And let me look at a little bit of math here. This is 1 minus a little bit over 1 plus a little bit. And if you kind of remember going back to 4th grade, if I put like 7 over 4, I might do some long division here and say, okay, you're asking how many times does 4 go into 7? And you would go, well, 4 goes into 7 one time. 1 times 4 is 4. Then you would subtract and get a 3. Then you might expand it out and say, okay, how many times does then 4 go into 3, you know. And of course you'd say none, so you bring down a 0, okay. So then you would say, all right, I've got a 4 into 30. Well, it looks like if I put a 7, that would be 28. Subtract the 2, I get a 2. Of course, that's smaller than 4, so I bring down a 0. And then I say that goes into 5 times. 5 times 4 is 20. Subtract those, I get a 0, 0. Okay, so after a bunch of long division, I can say that 7 over 4 is 1.75000000. Your author's going to do the same thing, but instead of using numbers, he uses symbols. So he says, all right, let's do some long division. On the outside, let me put 1 plus x. 1 plus a little bit. And on the inside, let me put 1 minus a little bit. And then you ask this question, and it's a little harder question than saying how many times does 4 go into 7, but it's basically the same question. And maybe we'll focus on the bigger ones first. How many times does 1 go into 1? And obviously, this is 1 plus an x. But maybe the first thing I would do is say, well, 1 time. 1 goes into 1 time. And then if I do, like we did down here, 1 times 4, and put a 4, I'd go 1 times 1 plus x, and then subtract the 2. Okay. So if I go 1 minus a 1, I get a 0. Okay. And then, of course, I have a negative x minus an x. So remember, this negative is distributed over both of these. So I'd say this is a 1 minus a 1, and this is a minus x minus another x. So that's 2x. It's a negative 2x. So you might say, okay, how many times does 1 go into a negative 2x? Well, obviously, that's negative 2x. 1 into anything. So that's why it's kind of nice to write it as 1 in a little bit, because it's always 1 into that, whatever that is. It's real easy. Okay? So back here, when I was doing the long division, I said, how many times does 4 go into 30? And I said 7. Okay, well, of course, again, what's nice is when you multiply this out, this first term right here would be a minus 2x. And then right here would be a minus 2x squared. So when you subtract it, this cancels. That negative and that negative now make a positive, and you would now have a 2x squared. All right, so how many times does this go into here? So you'd say plus 2x squared. And you could keep playing this game. I think you begin to see the pattern that forms. Maybe I'll do it one more time, but 2 times x squared would be 2x squared, and then plus 2x cubed. And then you subtract it. So this minus this is 0, and then you have a minus 2x cubed. And so you can see that the sign keeps changing as you go out. The 2 remained there, and the powers just keep getting bigger and bigger. So the next one will be plus 2x to the 4th minus 2x to the 5th. And the process goes on and on and on. However, here's where I think might be confusing you in the solutions, is your author is then saying 1 minus a little bit over 1 plus a little bit would technically be this long division, 1 minus 2 times a little bit, plus 2 times a little bit squared, minus 2 times a little bit cubed, plus 2 times a little bit to the 4th, dot, 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 dot. But remember, this x is a little bit, and so here's a little game your author is going to play here, which, again, might be some confusions to the solution. If x truly is a little bit, let me take a little bit. How about like 100, 0.01? So that's pretty small. But if I square it, it's super small. If I cube it, it is 1 million. So in other words, when you take 1 and you subtract this first number, even though you're adding something back, it is incredibly small to that. You don't really change it. And then you subtract something incredibly small from that. Again, you don't really change it. Then you add something even smaller back, and you don't change it. So you can say within the first couple of decimal places that all these other ones are irrelevant. They just show up in the millionth place, or this is the 10,000th place. They're just way out there. So the first 3 significant figures, this is all you need. And coming back to this problem then, that's essentially what we have right here, which I could replace down here. 1 minus a little bit over 1 plus a little bit. And so your author is going to say this 1 minus a little bit is approximately, and so that's the symbol with the little squiggly lines, equal to 1 minus 2 times that little bit. And what makes that a simpler problem to solve is the 1 shows up on each side. And now you can do a simpler calculation by just dealing with the little bits and seeing what you get. And of course, both of these little bits have a negative, so I'll ignore the negatives on each side, or cancel them off, I should say. And so 10 to the minus 7 is approximately 2 times v over c. Or put another way, the velocity then is approximately 10 to the minus 7 times c times a 2. And so I'll go 2 times 10 to the minus 7. And c is 3 times 10 to the 8th. Because if I put the 2 and the 3 together, I get a 6. And if I put 10 to the minus 7 and 10 to the plus 8, I get 10 to the 1. So that's approximately 60. I feel like I did something wrong, and I did. Yes. So thinking that was too much of a shift. It's right here. This 2 would be downstairs. 2 would be downstairs. Okay, let me try that again. So the 2 goes downstairs, and the c goes upstairs. All right. So the 3 over the 2 would be 1.5. And then the minus 7 and the plus 8 makes times 10 to the 1. So that's 15. I like that better. Yeah. It's got to be under 30 because of the little bit. All right. So, and that makes sense. About half of 30, 15. Okay, good. Hopefully that's helpful. All right. Bye now.